Hello and welcome to our physical sciences. Today my name is Themba Ncube. Our focus is on exploring electric fields, and it comes from the background of understanding what an electric field is, in terms of the region, in space around a charge, wherein if we subject that charge to a field, it experiences an electrostatic force. But then the more emphasis on today's session will be around net electric field at a point, whereby we know that around a point charge there is an electric field, and then if we put a unit positive charge, it experiences a force in that field. Now we want to see, or explore rather, and discover some of the exciting scientific facts around net electric field at a point due to more than one charge, which is something that comes from understanding what exactly electric field at a point is, and also understand in as far as in terms of the big question in today's session, to say what exactly affects the magnitude and direction of electric field at a point. Right. Let's quickly look at the background in terms of what we already know. Okay, so we know something, actually a lot, about electric fields now. We can also indicate or represent the electric field patterns around a positive charge, around a negative charge. Also, when two like or opposite point charges interact, we can represent that field using the electric field lines. And based on that, we also spoke about, in our previous sessions, we have managed to talk about, the properties of electric field lines, right? This is very important because every concept in terms of the force, the vectors, is a result of the field. So remember the properties of electric field lines and how the Coulomb's law fits into the concept of electric field at a point, right? Remember, in an electric field, if we place a unit positive charge, we can get an indication of how strong the field is at that point. But it is purely based on Coulomb's law, and we managed to say that as long as we know the magnitude of the force that creates the charge, and we know that electric field at that point, due to a charge that creates the field, is equal to the Coulomb's constant multiplied by that charge that creates the field, divided by the square of the distance, right? So today we'll explore more about E net in terms of the net electric field at a point, right? And then the big thought about, or the idea that we need to be comfortable on in terms of what we want to achieve. We want to also discover what are some of these important factors that affect the magnitude, okay, and direction. Already we are saying it's a vector of electric field at a point. So what exactly affects the magnitude and direction of electric field at a point, right? Now, having said that, let's look at the terminology. When you talk about the key terms or the terminology, these are definitions, which are basically all or nothing. So the language in science is purely grounded in the terminology. So we need to be very comfortable with the keywords in the definition, and we need to use the keywords in the correct context. That cannot be emphasized even more, because we have always said that once you are given a definition, it's a all or nothing kind of a scenario, right? So the keyword that I want us to first unpack and maybe remind ourselves of is electric field at a point, which is a physical quantity denoted by uppercase E, right? E stands for the unit. This is the symbol of the unit of electric field at a point, which is the force experienced per unit positive charge, right? The force experienced, okay, per unit positive charge, okay? So remember, when you talk about a unit positive charge, you are talking about the unit of charge, which is +1 Coulomb, right? So this is the force experienced per unit positive charge, which is a vector quantity. So emphasis is on magnitude as well as direction, right? So the emphasis is on magnitude and direction. So this is one of the vector quantities. So, and we know that this E, the unit is Newton per Coulomb, okay? And we also need to emphasize on the direction, okay? And remember the significance of the unit positive charge in terms of the direction. So we'd also use the simulation just to show, try and simplify this concept so that we understand it a little bit better. And then the word net is very common in physics. When we talk about the net, we're talking about, usually we would say it's the resultant, okay? Sometimes we say it's the total, okay? So the word net means total. Then what exactly do we mean when we talk about net electric field at a point? We're talking about E net. So what we indicated earlier is that, we can talk about the electric field at a point due to a charge that creates a field. But then if there are multiple charges, then we can talk about a point and how strong the field is at that point due to those two, point charges in space. And then hence would refer to it in terms of the net electric field at a point, right? Okay, so that's as far as the definition is concerned. Very, very important, okay? So electric field at a point is a vector. That's the main idea. This is the science around it. Otherwise, what follows after that is just the maths in terms of the calculations. So E is a vector, so it's an indication of how strong the field is at that point. Say, for argument's sake, we've got a point in an electric field which has got a magnitude of 10, okay, newtons per coulomb, just for argument's sake. Okay, let's say this is E1 at point 1, and then E2 at a different point, let's say, for argument's sake, is half that, which is 5 newtons per coulomb, whatever the direction is. What that simply means is that the electric field strength, or the electric field at point 1, is such that the force experienced is, this means that 1 coulomb of charge, okay, 1 coulomb of charge, okay, experiences a force of 10 newtons, okay? It experiences a force of 10 newtons, right? This is what exactly we mean when we say the magnitude of electric field at a point is 10 newtons per coulomb. So the unit positive charge, which is this plus 1 coulomb, experiences a force of that magnitude at that point. That's very important to actually bring an understanding into these figures or talk the science behind the numbers, okay? Now, equivalently, 5 newtons per coulomb at E2 would suggest that the force experienced by the unit positive charge is actually 5 newtons, which is half, or in the case of point number 1 in the same field, okay? Now, the force that will be experienced by a unit positive charge at a point due to a charge or multiple charge is the net electric field. So we are emphasizing the big idea around net electric field at a point. So this is, we identify a point in the field of more than one charge. Now, there are multiple charges, exerting a force on the unit positive charge at that point. So as a result of that, we can talk about the total or the combined effect of the forces exerted by the two charges at that point on the unit positive charge, which is our test charge, if we may call it that way, all right? So that's the big idea behind E net, which is primarily our focus for today, right? Now, say for argument's sake, X is a point, okay? So X is not a charge, it's a point. That's very important to make that distinction at a distance r meters from the charge Q, okay? So we've got charge Q, and then we've got a point X, which is a distance r from the charge Q that creates the field. So if the magnitude of the electric field at point X is 5 Newton per coulomb, okay? So E at point X due to Q1 at X, okay, is equals to 5 Newtons per coulomb, right? Whatever the direction is, okay? Now we just want to explore some understanding here behind the concept of electric field at a point. It says here, predict the effect of the following changes on the magnitude of electric. So our focus for now is the magnitude for now, okay? What if we're changing the distance to 2r? We double the distance. We want to understand exactly what happens. So I just want us to think about in terms of, at a basic level, if we double the distance between point X and the charge, what's going to happen to the electric field at that point, at the new point, which is twice the distance? Is it going to increase, decrease, or remain the same? So this is where we start. And then if we eliminate based on our understanding of the concept involved, I think then we are able to say, okay, then definitely if we increase, we expect it based on the mathematical relationship. But before we do that, let's look at a simulation just to give us an idea of what it means to double the distance, right? Okay. So we have a scenario here, okay? We have, let's use any type of charge. It could be a positive point charge, right? So around that positive point charge, what do we have? We actually have the electric field, but this electric field in this case is actually away from the charge that created the field. So that's the direction. So if we put a unit positive charge at some distance, that's what is going to happen. It will be repelled away from that charge which created the field. Now the issue here is about distance. Let's say for argument's sake, okay, let's say for argument's sake, we double this is the initial distance. Okay, that's our tape measure there. Okay, the tape measure says, okay, okay, sorry.
I tried, sorry.
It's fine.
You can just go back to the tape measure.
Okay, should I go back?
I don't know, Oscar?
No, it's fine.
Sorry, guys.
It's fine, Colleen.
I sneezed. I'm sorry.
Okay, we started on top of that.
That tape measure.
Should I start on top of this?
It's fine. Yeah.
Tape measure?
Huh? Yeah, we can start from yeah, you can reset it.
From the tape measure?
Yeah, reset it.
Okay. Is it fine like that? I want to start here. Yeah. Or should I, is it fine?
Yeah.
Okay. All right.
But 4 minutes.
Left?
Yeah.
It's fine. Okay. On your count?
Okay, 3 to enable 1.
Right. Now, this is the direction as indicated by the tail head, of the force that the unit positive charge will experience as a result of the charge that creates the field. Now, I'll measure the distance roughly. Okay, here's our tape measure. Okay, I'll try to measure that distance. Okay, something close to, okay, like 73.2 centimeters. Now, if we double this distance, what are we expecting? We're expecting something in excess of what, 146 or 0.4 centimeters, which is 73.2 as an example. Okay, I'll remove that. Let's move that further away. You can immediately see what is happening to the length of the tail, which suggests something about the what? The direction, about the magnitude, right? 146, something there, or 145, 144. Okay, if I put it there, you can tell already if the distance is doubled, the magnitude of the force experienced by the unit positive charge decreases. Okay, but it should be informed by some form of mathematical relationship that exists between electric field at a point and the distance. Okay, going back to our question. Now we have doubled the distance. What do we know? We know that E is equals to Q over R squared. So if the force, if the charge is Q and the distance is R, what have we done now? We have doubled the distance. So we are told that this is 5 newtons per coulomb, okay? Right? So this is 5 newtons per coulomb, in other words. That's our magnitude of E, which is electric field at a point. So if we double the distance, what happens there? We get the new force in terms of 5 is going to be Q, because the charge is still the same, we've doubled the distance. Now we are squaring that double distance to give us k q over 4r squared, right? Immediately I can tell, okay, now this is like a quarter of k q over r squared, of which this is, we know that this is represented by 5 newtons per coulomb. So already we can tell that this is a quarter of 5 newtons per coulomb, which is 5 over 4 newtons per coulomb. Now already you can tell that the force experienced by a unit positive charge actually decreases, right? So if you change the distance, the new force would be 5 over 4, okay, which is like 1,25, okay, which is a quarter of that. So it's going to decrease to 5 over 4 newtons per coulomb. So neither does the force increase or remain the same if we double the distance. The force will actually decrease, but it's in proportion with the mathematical relationship that we already know. So this is just a basic idea in terms of how does the distance from the surface of the charge that creates the field to the point in the field, how does it affect, when we vary the distance, how does it affect the magnitude of electric field at a point? That said, let's take a short breather. We'll explore more of these, manipulations as we go ahead. Let's take a short break for now.